Mueger from Nijmegen, and he will give a nice old-fashioned whiteboard.
Thank you. Well, thanks to the organizers for inviting me. As Bart said, the talk will be old-fashioned, at least in form, if I hope not in content. At least some of the results are brand new. So I will talk about modular categories and what I mean by that are modular tensor categories, but I will omit tensoring what follows. Okay, so what are they? Well, preliminary definition is they are a rather special class of braided tensor categories. And abbreviate that. And we have heard about braided tensor categories in the last talks. So I hope to convince you that modular categories are quite interesting. So why should one be interested in them? Well, first of all, they arise in conformal quantum field theory, and that's essentially where they really come from. They arise from quantum groups, and from two different purely categorical constructions, which I will mention. So there are a number of ways to get modular categories. So, and they have applications to topological as opposed to conformal quantum field theory in 2+1 dimensions. So if you give me a modular category, I can give you a topological quantum field theory, whatever this is. And that has been done by Radboud and Turaev in the early 90s. Okay, so this is one application. But now there has been recent interest in topological quantum field theory, since you can try to use them for topological quantum computation. I'm not going to say much about that. The idea is independently due to Michael Friedman of Poincaré conjecture fame and Alexei Kitaev. If I understand it well, Friedman's idea of departure was the fact that the Jones polynomial is NP hard to compute, so you could hope that if you have a TPFT you can do hard computations, whatever that means. Kitaev's motivation, I think, is different. He considered topological excitations in two-dimensional quantum spin systems and proposes to do quantum computing with them. The motivation being that as topological excitations they should be sort of protected against decoherence. So the ideas of departure of these two authors are quite different, but the underlying thing is that in both approaches you have a modular category sitting behind the whole thing. For example, Kitaev considered a very specific quantum spin system, which he calls the toric code, and showed that you really get a modular category which can be studied. It's more or less the most trivial modular category that there is, but at least this is realized in the quantum spin systems. Okay, I'm not going to say any more about topological quantum computing, mainly because I know very little. So I should say a few words about categories, tensor categories, braided tensor categories, and so on, but I can be very brief since Sean has done that. So I assume that everyone knows everything about tensor categories. All the categories I consider, at least almost all, will be K-linear, where K is a directly closed field. And usually characteristic will be 0 or even C. You don't need that for all results, but I don't want to invest time to say when you need which assumption. Okay, now in this situation I say that an object X is simple if end X is just K times the identity. Okay, and I will always assume that the tensor unit of your category is simple in this sense. And then again, most categories will be semi-simple, which means that every object is a finite direct sum of simple objects. Or highbrow definition would be that we have an abelian category with all exact sequences split. And I say a semi-simple category is finite when the set of simple objects, is this still legible if I write it? Perhaps not. If the set of simple objects modular isomorphism is finite. The standard example is representation category. Okay, so these are essentially the basic things about categories and terminology, and now I can, well, there is one thing I should say a few words about, namely duals. Well, if we have an object X, there should be an object X bar, which is a two-sided dual, and by that I mean that you have all these morphisms in both ways, and that's why I say two-sided. And the usual identities. Okay, one should really be more precise about duals. One should talk about pivotal categories and spherical categories. So these are assumptions on the duals in your category of increasing strength. But this is a technical subject and I won't go into it. The important thing for me about duals is that they allow us to define traces. So if we have an endomorphism of some object X, then we can define its trace, which is an endomorphism of the unit object. And since I assume the unit object to be always simple, I can identify this with K. So to every endomorphism of an object, I can associate a scalar. And in the category of vector spaces, finite dimensional vector spaces, which has duals, that is the ordinary trace of endomorphism. Okay. So now, just as a matter of terminology, a fusion category, that is a finite, semi-simple, K-linear tensor category with two-sided duals. Well, in principle I want more, I want the category to be spherical, but okay. So in particular, when I have traces of endomorphisms, I can for every object consider the trace of the unit morphism, and that is called the dimension of the object. And if I have a semi-simple category that is finite, so it has only finitely many simple objects modular isomorphism, I can also define the dimension of the category, and that is defined as the sum of the squared dimensions of all irreducible objects. So capital I is a set representing the isomorphism classes of simple objects. And, well, if H is a finite dimension semi-simple Hopf algebra, then as you probably know, the dimension of the category as defined by this is just the dimension of the Hopf algebra, which of course motivates the terminology. Okay, so now we can get started. Now I will be interested in braidings, which have already been introduced, so I don't need to say much. So the point is that for every pair x and y, I have a morphism cxy from x tensor y to y tensor x, which is an isomorphism, so I can commute objects, and that should satisfy some identities, which are sort of non-trivial to memorize, but becomes easy if you look at a diagram. Sean told you that such a picture can be interpreted in two ways. It can be interpreted as the braiding between x and y tensor z, but also as a composite expression involving the braiding of x with y and the braiding of x and z. So I don't write down the precise formula. And I should say that I am optimistic, so my diagrams go upwards. But that's not so important, since I won't draw any. Okay, now the important thing is that if I compose braidings twice, I get an isomorphism of x tensor y, and this need not be the identity of x tensor y. I mean, that's the whole point of the talk. I say C is symmetric if, well, this thing is the identity for all tensor y, and symmetric categories, of course, are a well-known notion that has been around since the early 60s, whereas braided but not symmetric categories have been around only since the late 80s, because there are no obvious examples. For symmetric categories, there are lots of examples. The category of sets, the category of vector spaces, finite dimensional or not, representation categories of groups of all sorts, they all are symmetric. But finding genuine braided categories is not so trivial, except perhaps the free braided category generated by one object, which I don't want to define now. Okay, so well, let's try to measure how non-commutative or non-symmetric a braided category is. And that is what I call the center, well, perhaps the symmetric center to avoid confusion, of a braided tensor category, which I would abbreviate like that. Namely, I call it Z2 of Z, and that is a full subcategory of C, defined by saying that the objects are those objects of C such that Cyx composed with Cxy is the identity for all y in C. Yeah. This is a subset of the set of objects, so I have a full subcategory. It is easy to see that this is a tensor subcategory because the braiding satisfies such identities. And it is also easy to see that this is in fact a symmetric subcategory. Yeah? So every braided category has a canonical full symmetric subcategory, and that is the symmetric center. And it is sort of obvious that C is symmetric if and only if it equals its symmetric center. Yeah? Okay, and now I can define what modular categories are. A modular category is a braided fusion category where fusion is all this finite, semi-simple, k-linear. If you don't like such a long list of axioms, just think of the representation category of the finite group over the complex numbers. It has all these properties. But now you also want a braiding, and there is one additional axiom, namely the symmetric center, rather than being equal to C, as in the symmetric case, it should be trivial. What do I mean by that? Well, it is very easy to see that the tensor unit is always contained in the center, and also all direct sums of the unit with itself are always in the center. And by saying the center is trivial, I mean that it contains only objects that are isomorphic to finite direct sums of the unit. Or every simple object in the center is isomorphic to the unit. That's another way to say it. Okay, so this is my definition of a modular category, and from the definition it is clear that they are sort of the opposite extreme among the braided categories to the symmetric ones, and I claim that they are equally interesting, if only a bit less familiar. So why are they called modular? Well, I could say because Tourayev called them thus, but he had reason for doing that. We define an element of our ground field K for every pair of object X and Y as the trace of this thing. As I told you, it's an endomorphism of X tensor Y, and so you can take its trace. So that's a number. You can do that with any pair of objects, but we look only at the matrix that you get by considering simple objects and only one for each equivalence class. So this thing is a matrix over our field of dimension equal to the number of simple objects. Okay, and now that is the fact if you have a braided fusion category, then C2 of C is trivial if and only if the matrix S is invertible. And that was the original definition in Tourayev's work. So he would have said braided fusion category with invertible S matrix, but triviality of the center is natural. And this equivalence was proven by various people. Okay. But still, that doesn't explain why I say modular. Well, I define a second matrix, also indexed by the simple objects, and I say you have a Kronecker delta, so it will be a diagonal matrix. And here I take the trace of the braiding of X with itself.
Might be time to change the pen.
Yeah.
Very good thing.
Okay, so if this is the braiding and you take the trace as a picture, it would be something like that. Or, since it doesn't matter whether you take traces to the left or right, it would be something like that. Okay, and now you prove that you have this matrix identity where alpha, beta are non-zero numbers, and C is the matrix which physicists would call charge conjugation. So it's the permutation matrix which flips objects with the duals. Okay. But it should be sort of clear that this defines you a projective representation of the group SL to Z. The 2x2 matrices with integer entries and determinant 1. Since this thing has two elements S and T, satisfy the same identities. Yeah? So having matrices satisfying this gives you a projective representation of the modular group. Yeah? This thing is the modular group. And that's why the categories are called modular categories. Okay. And modular actions of the modular group play an important role in conformal field theory. And as I said, modular categories come from conformal field theory, but I don't have the time to go into that.
Is it PSL2 or is it?
No, that's the ordinary SL2Z. You would get PSL2Z if C is the unit matrix. And of course there are categories where every object is self-dual. And then you get representation of PSL2Z. Okay. So this representation of the modular group is a bit mysterious, so let me just say one more word. I mentioned that Reshettikin and Turayev associated to every modular category a topological quantum field theory in 2+1 dimensions. Well, that's in itself a complicated object, but in particular that means that for every closed two-dimensional surface you get a representation of the mapping class group, and the mapping class group of the two torus, T2, is just the modular group SL2Z. So the representation of the modular group obtained by simply looking at the matrices S and T really is the one associated by the TQFT to the two torus. But this is a big story and I can't say more about that. Okay, so what can be said about this representation of the modular group? Well, it is a projective representation, but you can always make it into a proper representation by rescaling the matrices S and T. But this is non-unique, you have 12 different ways of doing it. But in any case, it has been shown that let pi C be the representation of SL2Z to and this is just the representation that I have constructed here. Then it has been proven very recently, 2 years ago, that pi C of SL2Z is always finite. So this representation factors through a finite group, and what is almost always true is that the kernel of pi C contains a congruent subgroup gamma of n, which is defined as the elements of SL2Z, which are congruent to the unit matrix modulo the integer n.
Sorry, what's this k to the I in brackets here?
Well, that's just the k vector space of this dimension, where this is the number of simple objects in your category, since that indexes the matrices S and T. Yeah? And one can prove that the kernel of this representation always contains a congruent subgroup. This subgroup has finite index, so it implies the first statement, but it is somewhat small. These are number theoretical things that have been conjectured for a long time and known to be true in conformal field theories, but now it has been proven abstractly for every modular category, and this is due to and shown in the book. Okay, but that's all I want to say about this modular representation. I just said that to explain the name of these categories and to illustrate that they have lots of connections with number theory and so on. Okay, now we would like to understand modular categories, and so we would like to prove some results of structure theory without looking at particular examples, some things that are always true, sort of like this. We would have ways to construct examples, and we would like to classify them. is going to be difficult. So let me begin with the first, some structure results. Okay. Is this still? The next definition is relatively general. It works for every braided category. And D is just some subcategory. Whether monoidal, full, or whatever, it doesn't really matter. And I define the centralizer of that subcategory, and I denote that like this. The relative commutant, if you want, of D in C. This is a full subcategory of C. And its objects are just the X in C. And now this is just generalization of something that we have done before. Here we look at all objects Y in D in the subcategory. And the full subcategory is that of objects which commute in the sense of this identity with the subcategory. So in particular, the center of a braided category is just its own centralizer. But this generalizes the notion. Okay. Now, what one always has, and from now on I will simply write D prime instead of this relative notion, that D always sits in its double commutant. That is the same as for matrices, for example. But in general, there is no reason why this should be an identity. So there is a more specific result. These pens are not great. If C is modular and D is a full monoidal subcategory, and let's say it is replete, so it is closed also under isomorphisms. And then, if I take the commutant twice, I get D back. So not just an inclusion, but really get the whole thing. And I have this nice identity on the dimensions. So the product of the dimension of the subcategory and of its centralizer is just the dimension of the whole thing. And these things together I call the double commutant theorem, in analogy to theory of phenomenon algebras. Okay. But you have more. Yeah?
Would you call this a sure by duality also?
No.
Okay.
No, I don't think this would be appropriate here. Now, I mean, there is a classical theorem like that. If you have a matrix algebra and a subalgebra and take the double commutant, you get the original thing back. And of course, that is true for phenomenon algebras. But sure, why? Anyway, now let's look at the case where both the ambient category C and the subcategory D are modular. Then also the commutant is modular. And the big category simply is the direct product to D and its commutant. So whenever you have a modular category and a modular subcategory, then the subcategory is in fact a direct factor. Yeah? And this is a much stronger result than what you have in group theory. If you have a finite group, you have a full subcategory of the representation category that corresponds to a quotient. That is the representation category of a quotient of the group, so you have an exact sequence. But of course there are non-trivial, non-splitting exact sequences for finite groups. For modular categories this doesn't happen. Whenever you have a subcategory, you have actually a factorization of the category. it is natural to say that a modular category is prime if it doesn't have proper modular subcategories. In other words, every full modular subcategory is either trivial or the whole thing. You know, just like for prime numbers. And then you get that every modular category is equivalent to a direct product of prime ones. Okay, and there is no extension problem as there is for groups. So classifying modular categories is just the same as classifying prime modular categories, and then you are done. But of course that is still a difficult problem. So let me give you examples of prime modular categories.
Sorry, is the decomposition unique or not?
No. No. This is, well, it is non-unique in general. So let me give you some examples. If G is a finite, simple, and non-abelian group, then by looking at its quantum double, and I will say a few words about that later, but I think Sean has already said that, then this category is modular. Well, that has been known for a very long time, but it is also prime. So every finite simple non-abelian group gives you a prime modular category, and they are all non-equivalent. But if G is abelian, so let's say finite abelian, then in general this thing is not prime, even if A is simple. So here the problem already starts. One can show, to give one positive example, if every object, every simple object in C except the unit has dimension bigger than 1, which is the same as it doesn't have a tensor inverse, non-invertible, then the factorization of C is unique. So the non-uniqueness of the factorization, in a sense, comes from the existence of invertible objects, and that is not so hard to understand, at least intuitively. If you have a factorization, then you may possibly move simple objects from the left to the right and get a different factorization. That this really is what happens, I can't really go into, but at least you have this result.
Excuse me. So, a little bit back, we were talking about the primes on the D, the commutant categories. Sorry, did you define that, or did I miss that definition?
Yeah, sure. Let's see.
Oh, sorry. Thank you very much.
I said that, I mean, this would be a more correct notation, but I'm just abbreviate like that. Okay, so these are some structural results. Okay, but now the question is, how do we construct modular categories? I already gave one example, but that was sort of ad hoc. Quantum doubles of finite groups, and they are very classical examples. So let's look at this thing a bit more systematically. Okay. So that was the second point on my list, constructing modular categories. And And well, I will briefly look at 4 methods. The first one, let C be a braided fusion category. And as I said, a modular category is just a braided fusion category with trivial center. So non-modularity is due to non-triviality of the center, and you could think of dividing out the center in order to get a modular thing. I put that into quotation marks since the construction that can actually be done is quite complicated. Yeah? So the slogan would be dividing out the symmetric center and hoping that this thing will be a category with trivial center and therefore modular. And that has been done independently by Bruyère and myself around 2000. Okay, but this is only partially satisfactory. The point is that if C is symmetric, well, then C is equal to its center, so if you divide that out, you get a trivial category. And by the trivial k-linear fusion category, I just mean the category of finite dimensional k-vector spaces. So the problem is, in order to get a non-trivial modular category, you need to put in a braided category that is not entirely symmetric. So you need something that is braided to begin with. Still, this is a useful construction which has applications, but okay. So the second thing is conformal quantum field theory, and more precisely, chiral conformal quantum field theory. And there is a subclass called rational, and such things actually give you modular categories, which has been proven in 2 different axiomatic settings, namely an operator algebraic approach, and that was done by Kawahigashi, Longo, and myself in '99. So if you have a structure that can be called rational chiral conformal field theory in some precise axiomatic setting, then you can prove that the representation category of that thing is a modular category. Of course, conformal field theories are themselves quite complicated objects, so in order to get modular categories, you need a conformal field theory. But I should at least mention that a similar result has been obtained for vertex operator algebras by Huang around 2005. Okay, but there is a special class of rational conformal field theory, namely the ones arising from loop groups. Okay, and what does that mean? Well, here your point of departure is a compact, simple Lie group, like SUN, and an integer k in n, which you call the level. Yeah? And from these 2 data you can construct a rational chiral conformal field theory in either of the 2 settings, and therefore you have a modular category. Of course, this is way too complicated to say more about that. In the operator algebra setting, the construction of these conformal field theories has been done by Anthony Wasserman, Cambridge. Okay. So at least here you have a family of modular categories associated to a pair consisting of a simple compact group and an integer. Now, these categories can be constructed in an alternative way using quantum groups. Namely, you let G be the Lie algebra of G. Poynting algebra, you Q-deform it in the sense that Sean mentioned. And you do that in the case where Q is a root of unity. And after enormous effort, you get a modular category. And the nice thing is that the modular categories that you get in this way are the same as the ones you get from loop groups via conformal field theory. Yeah? So you can get these categories by essentially purely algebraic methods without using quantum field theory. Okay. And now I will come to the last thing, that is the quantum double construction. And here I can be relatively brief since this has been mentioned before. Namely, if H is a finite dimensional Hopf algebra, Drienfeld constructed a new finite dimensional Hopf algebra whose dimension is the square of the dimension of H, together with an R matrix, whatever that is. So this pair is a quasi-triangular Hopf algebra. And the point is, well, you have a Hopf algebra, so the representation category is again a tensor category, and the R matrix is precisely what you need to make this tensor category braided. Yeah? So you get a braided tensor category. Of course, you would like the category to be semi-simple, and that is the case if and only if the quantum double is semi-simple, and that is the case if and only if H is semi-simple, at least in characteristic 0. Okay, but the fact is, if H is finite dimensional and semi-simple, and I do that in characteristic 0, then the category of H modules over the quantum double is modular. And I think that was first proven in a paper by Etinghoff in Gelaki. They use that for some other constructions. Okay, but this is a Hopf algebra construction, and I am more interested in more general tensor categories. So this construction has a purely categorical analog, and that is the center construction. Apologies for numerical spelling. And this is due to various authors, one of which is in the audience, Sean Majid, and unpublished work by Drienfeld, and I think also Joey Allen Street had something to say about this construction. So the point is this: if you have a tensor category C, then you put it into some machine, and what you get out is what I call C1 of C. Note the C1 to distinguish from the earlier center C2, and that is a braided tensor category, which I abbreviate like that. Okay, so let me tell you in a few words what this construction does. Now, so let C be a tensor category, X an object in C. Then I say a half braiding for X is a family of isomorphisms. Ex of Y from X tensor Y to Y tensor X, where I look at all objects Y in C. Yeah? So this X is fixed, since I'm talking about a half braiding for X. But then, for every other object Y, I want an isomorphism from X tensor Y to Y tensor X. And this has to be natural with respect to the argument Y, and satisfy one braid identity, namely if I do that with y tensor z, well then this thing should be expressible in terms of ex and y and ex of z in precisely the same way as in the first braid identity, which I didn't write down, so I don't want to do it here. Okay, so this is a half braiding. I mean, it is clear that for a given object x, there may be no half braiding, perfectly possible. But nevertheless, we now define C1 of C is the category with objects, the pairs x, ex, where x is an object in C, and ex is a half braiding for x. And this has at least one object, namely x the identity and ex the identity morphism of y, so it's at least not the empty category. But of course I need to say what the morphisms are. So I have to define what the Hom sets are. And it consists of those morphisms from x to y in the original category that are compatible with ex and ey. And what that precisely means I don't want to write down, but it is pretty easy to figure out what it means. And we want a tensor category, so I have to define a tensor product. Well, it is just the tensor product of these objects and a new half braiding, where this half braiding is defined for every object z. Well, in terms of course, ex of z and ey of z, so the half braidings of the objects x and y. And again, there is essentially only way to do that. And if you have done this, well, you need the unit object, but I already said that. It's given by this. So what you obtain is a tensor category. But this tensor category actually has a braiding. Namely, you say that the braiding for the pair x, ex, y, ey is just ex of y. This looks non-symmetrical, but it works. We could also use ey of x inverse, but we take this. Okay, so what we get in this way is a braided tensor category, and the fact is that really this is a generalization of the Hopf algebra construction, namely if H is a finite dimensional Hopf algebra, then you find that if you apply this categorical construction to the modular categories, which is a tensor category, you get the representation category of the quantum double, and this is an equivalence of braided tensor categories. I actually don't know who proved this first. Anyway. But I mean, so for finite dimensional Hopf algebras, the categorical center of this tensor category is well understood. You can describe it in Hopf algebra terms. But for a general category, you know essentially nothing. You only know that it always has this unit object, but otherwise it's really empty. And still, as far as I know, there is only one result, namely something that I don't know, let's say around 2005. Let C be a fusion category over some algebraically closed field with dim C non-zero. Then Z1 of C, well, you prove a number of things. It is semi-simple, finite, so it has only finitely many simple objects, you can actually compute the dimension of the category, and it is the square of the dimension of the original thing, which is what you expect if you look at the Hopf algebra situation, but the proof has nothing to do with the Hopf algebra one. And the category is modular, which you could express by saying that C2 of C1 of C is trivial. Of course, it's tempting to believe that such things can be generalized, and I believe it is true. Okay, so by this result you get lots of modular categories, but not every modular category is Drinfeld or Majid or whatever center of a modular category. This is quite important, since one could go as far as saying that the modular categories obtained in that way are the trivial ones, sort of the least interesting. Perhaps that is a bit too radical, since there is one very nice result about that construction which has been proved just this year by Tourayev and Virelisier, former PhD student of Tourayev. Well, if you have a fusion category, its categorical center is modular, and to every modular category you can associate a 2 plus 1 dimensional TQFT. The Reshetikhin Tourayev TQFT associated with the modular category C1 of C, where C is fusion, is isomorphic to the Tourayev, Viro, Barrett, Westbury, and the list goes on a bit, TQFT associated directly to the fusion category C. Yeah? The point is that there are two different known ways of constructing TQFTs in 3 dimensions. One of them is the Reshetikhin Tourayev TQFT, where you need a modular category as input, and there is another one where you just need a fusion category as input. And that started out as the Tourayev-Viro construction, which was generalized by Barrett and Westbury and also by Gelfand and Kachdan, and that is the second thing. And these TQFTs coincide, and they are connected by the center. So that's another nice thing, and it was proven this year. Okay. Pardon? 5 minutes, okay. So, I won't get to the end, but I can tell you what the cost is. Well, what can you say about Z1 of C when C is already braided? Yeah, this construction was meant to construct braidings, but of course you can't do that with a category that is already braided. Well, then you can get a factor that associates to every object X a pair in the center, like that. You just use the braiding. Of course, a braiding restricted by fixing one argument is a half braiding. So, and this is full and faithful braided tensor functor. In other words, you have an embedding of C into its categorical center. So now assume that C is also modular. Well, then, of course, this will be modular. So we have an inclusion of modular categories, but that means we have a factorization. Yeah? Z1 of C will then be equivalent to C tensor C tilde, where C tilde is the same tensor category as C, but with braiding defined in that way. So that's the one that you get by passing from, let's say, overcrossings to undercrossings. And in a modular category, these things are not the same. Yeah, so that was also an old result of mine. And now that we want to classify modular categories. So what can we do? We get lots of modular categories from the categorical center construction, but there is no hope of classifying all these categories, since there are simply way too many fusion categories. Okay, what helps a bit is that there can be non-equivalent fusion categories which have equivalent categorical centers. I don't have time to go into that, but still that doesn't help. There are still too many. So the idea is classify modular categories modulo centers. So the things of the form C1 of D. And now something happens. So let's define a precise equivalence relation. We say if C1 and C2 are modular, we say that they are equivalent by definition with respect to this equivalence relation, if and only if there exist fusion categories, so not necessarily braided, such that C1 product with the center of D1 is equivalent to C2 modulo the center of D2. And here I mean the equivalence of braided tensor categories.
Can you come to a conclusion?
Sure.
Yeah? It is clear that in this way you have gotten rid of the centers, since every category of that form is equivalent to the trivial category. And now the remarkable thing is that if you define modular categories modulo this equivalence, this is an abelian group where the product structure comes from taking direct products of categories. And well, this is really the last thing I should say. If you take the equivalence class with respect to this equivalence relation, you need an inverse to be able to talk about a group. And you just take C tilde, the category with a flipped braiding. Namely, if you multiply this element and this, that is the equivalence class of that object. But for a modular category, that is a center, and therefore, in this equivalence relation, it is the unit. So you get an abelian group, and we call that the width group of modular categories. I should say that this is joint work with Alexei Davidov, Viktor Ostrik, Dmitry Nikšić, 2 months or so old. We call this abelian group the width group since it contains a very classical thing known as the width group, about which I can't say anything. And we conjecture that this group is generated by the equivalence classes of the categories coming from quantum groups. But this is the conjecture.
Very good. Thank you very much. Any questions about this? Yes.
Is your last construction a sort of Morita things? Where you put this tensor Ds to...
I wouldn't call this Morita equivalence. I defined the notion of Morita equivalence of fusion categories long ago and proved that Morita equivalent categories have equivalent centers, and in the meantime also the converse has been proven. But that is a different equivalence relation, since this is an equivalent relation of modular categories and not just of tensor categories.
Jamie, you had a question?
So if you have two modular categories and you have functors between them, most of the time you can decompose those modular categories, domain and codomain of that functor into their primes, their prime factors, in a sort of unique way out to these simple objects. Can you also decompose the functor in between them in a useful way?
I haven't thought about that.
Okay.
essentially all the root of unity categories are not centers. I mean, there is a nice characterization of the modular categories that are centers, but I have no time to say that.
Well, just to sort of remark on that, I mean, the point is that the quantum double doesn't give you all quantum groups of that type, but they're all quotients of the quantum
Right,
double.
true.
So all your other examples might very well be related to the
Well,
center line.
I mean, of course, it is true that every modular category is a full subcategory of the quantum double, namely by taking the quantum double of the category itself.
Yeah.
But that doesn't help you classify them.
Okay, let's thank Mikael again.
Okay, so tomorrow this door will be locked and there's no receptionist to let you in.